All right, hello everyone. My online students are kind of used to the video lesson, but welcome to my in-class data management group as well. Hope everybody is doing well. This will be the first video lesson I'm posting since we haven't been at school after March break. I'm going to try my best to upload a video lesson and some practice every day. It might not be every day. Some days might be a lesson with a lot of new stuff and concepts, and another day might just be an application, some fun examples. And generally for now, the focus will be on learning and not so much on evaluating what you're doing. If I get any instruction otherwise, especially for my online course, because you guys are used to kind of getting evaluated remotely, I'll certainly let you guys know in our news feed. But for now, my hope is that you guys just stay busy, try to keep learning, and fill your day being productive. Because I think, like, personally, having something to do that's meaningful, that advances our courses, and it's a lot better than just like kind of just sitting around and waiting for the self-isolation to end. So today's video lesson is on probability distributions. This is the start of our third unit, let's get going. So we did cover a unit on probability, and that was focused on the probabilities of individual events. For example, like probability of rolling 10 with a pair of dice, or the probability of winning $10,000 in Plinko. In this unit, we focus on developing models for what we call probability distributions. Probability distribution, it shows all of the outcomes of an experiment and how they're distributed. So we're not going to focus so much on an individual event, but focus on all events and how those probabilities are distributed. Some definitions to get out of the way. First, we'll be talking about random variables a lot. A random variable is a quantity that can have a range of values. Often we'll designate that by capital X, and individual values will be designated by a lowercase s, x. So for example, for rolling two dice, my discrete random variable x might be the total on two dice. But when we get into actually analyzing probabilities, so you guys know, so the probability of that little x is equal to, well, I should say 2. You can't get total of 1. The probability that total on two dice is equal to 2, I've used lowercase there. We've revisited it. We've done this in the past. It's 1 out of 36. That notation is, won't have to worry about it too much. But yeah, generally capital X when you're referring to what your variable is, lowercase x if you're referring to an actual value. Our unit, this unit focuses on discrete random variables. A discrete random variable is a variable that can only have certain values within a given range. So sum of two dice is a discrete random variable because you can only get so many totals, certain values. You can get 2, 3, and a total all the way up to 12. Those are the values, only certain values. Whereas continuous random variables, these are variables that have an infinite number of possible values in a given range. Often these are measurements like volume or time. For example, we talked about someone's height. Like, what are the possible values for someone's height? Like, we know for total on two dice, like you can get 2, 3, 4, 5, 6. You can just write them all down. Can you write down all the possible heights of somebody? Well, no, you can't. There's infinitely many, right? Because like somebody could be 180 centimeters tall, or 180.1 centimeters tall, or 180.01 centimeters tall. And even in between any of those, there's an infinite number of possible heights. So this is a continuous random variable, and we actually look at those in a later unit. So why don't you take a moment? I've given you 5 variables here. Would you guys consider these discrete or continuous? If you want to pause the video, just have an idea, you can unpause it when you're ready, or you can just follow along right now. So rolling a single die, hopefully that was a slam dunk for you guys. That is, I'll just put a D here. That is a discrete random variable because you can, on a single die, you can get 1, 2, 3, 4, 5, or 6. For rolling a pair of dice and recording the total, we just talked about that is discrete. You can only have the totals 2 up until 12. Measuring length of time. So somebody waits in the store. Yeah, and for shooting these in my basement at home, I'm not gonna, if I make a mistake, I'm not gonna reshoot the video because it just is what it is. Time is limited. Got 2 boys running around the house. You might hear them at some point, but yeah, we're gonna do the best we can. Time is a measurement, and that would be a continuous random variable because there's, even in between 5 minutes and 10 minutes, there's infinite times you could list. 5.1 minutes, 5.01 minutes, et cetera, et cetera. Measuring someone's height, just talking about that one, continuous. There may be some discussion with shoe sizes. So in North America, we denote shoe sizes by either whole numbers or half values. So for example, I'm not sure how low they go, but you have size 6, size 6.5, size 7. Like Shaq has like size 22, 22.5 feet. But like, there's only certain values. You can't have a shoe size of like 6.75 or 8.102. This is a discrete random variable. Again, our focus this unit will be on discrete random variables. Let's dive into some examples, kind of getting more involved as we go. Ultimately, this one is going to be a very simple example. We have a spinner here. So you can imagine some simple child's game, like Life uses a spinner, lots of simple games out there. This, you can also think of this one as almost like a 5-sided dice. Just basically there's 5 equal sections. Each space is equally likely, and the spinner tells you on a board game how many places you'd move. So we're going to analyze this distribution of this simple game spinner. We're going to list all the possible number of moves and determine their probabilities. And we'll make a sketch of this probability distribution as well. So because it is a spinner and all of those sections are equally likely to get hit, the probability of getting each number of moves is 1/5 or 0.2. Doesn't matter what whether you use 0.5 or 0.2, since they're exact values, 0.2 seems easy. And that is one way to show a probability distribution, is to make a table. So we have created a probability distribution. So I'm just going to put a little 1 there. That's one way to illustrate a probability distribution. A second way of illustrating the same information is to make a probability histogram. So I'm just going to put a 2 here. So this is an alternate way of displaying the same information. So a histogram is just like a bar graph. And we're going to, because this is a discrete distribution, we're going to put bars at each value. So the probability of getting a 1 is 0.2, of getting a 2 is 0.2. And the bars will not touch because these are discrete, kind of separate values. So it's a very simple probability distribution. All the probabilities are equal. In fact, a distribution like this, where all the probabilities are equal or the same, has its own special name. It's called a uniform distribution. So a simple spinner like that, or rolling a single dice, is a uniform distribution because each side of a dice has a 1 in 6 chance of being rolled. Flipping a single coin is a uniform distribution. The probability of heads or tails is 0.5 or 0.5. And the graph of a uniform distribution will be like so, where all the bars are the same height and it's just basically a horizontal line, which kind of makes sense. Take a moment, add up all those probabilities in the right-hand column. What do you get? And think about what you get and why it makes sense. So you can pause that, quickly do it. I mean, most of you guys could probably just have a little mental math, but 0.2 plus 0.2 plus 0.2. If you add all those up, you get 1, which kind of makes sense, because if in a probability distribution, you're listing all the outcomes and the probabilities of each of those outcomes, they should add to 1 or 100%, because you're counting all the outcomes. So it's actually a key idea that the probabilities in any probability distribution add to 1. All right, let's move forward with a more involved example. Let's make a 2-dice distribution. Now, you guys have already analyzed the probabilities of rolling a total, rolling 2 dice, recording the total. The possible totals are 2 to 12. So I'm just going to list them here. 2, 3. So these are all the possible outcomes to lowercase x. 8, 9, 10, 11, 12. And in this case, our discrete random variable x is the sum of 2 dice, capital X. Each tick on this graph is vertical tick is 1/36. Couldn't figure out a way to get that display nicely as like fractions over 36. So there it is. So 0.027 repeated. That's actually just 1/36. And we should be able to get a nice visual of this distribution here. We don't need to go back and prove all this. We've analyzed 2 dice completely from our earlier unit on probability. So if we just want to quickly get this down, there was a 1 out of 36 chance of getting a total of 2, and then 2 out of 36, and it increases up until the highest probability was 7. Getting a total of 7 was most likely. It can happen 6 ways out of all 36 possible outcomes, or 1 out of 6. But as we'll see in a minute, there is value in leaving things as with a common denominator, even if you could simplify those guys. And then finally, a 1 out of 36 way of getting a 12. So we have created, this is the probability distribution for rolling 2 dice. That is one way to display it. A second way is with a probability histogram. So we'll often do both just to see how probabilities are distributed. So here we'll start at the 2. The chance of getting a total of 2 is 1 out of 36. Again, that was 0.02, et cetera. And then it's actually pretty easy to draw, because for 3, it just increases by 1. Okay, I'm on my tablet here, so my bars might not be perfectly straight. You guys just do your best. Again, it is what it is. 6 is 5 out of 36. And then 7 out of 36. And then they start to tick back down. So you can see it's definitely not uniform. All the probabilities are not the same. They're all different. But there's a nice symmetry to this one. And finishing it off. So yeah, it's a nice way to show all the outcomes and their probabilities. You can see which one is most likely. You can see the tie, which ones are less likely. So we have completely described this distribution. Later on, we might revisit SumSwamp and look at the distribution for that and how it's drawn, because it was not perfectly symmetric like this guy is. And we might do other interesting scenarios too. It may be worth your while. Anytime I create a table, it's worth a check just to make sure those probabilities all add up to 1. And in fact, these guys do. We verified this earlier, but that does add up to 36 out of 36. We kind of know we did it right. But now I want to take this further. Go back to that distribution on 2 dice. Can you predict what the average roll would be if you rolled 2 dice? Let's say you rolled it thousands of times and recorded the sum. What would you expect to get on average if you averaged all those totals? So take a moment, think about that. You can use the table, you can use the graph. What do you think the average roll would be? All right. Well, it turns out to be 7. And many of you guys probably saw, hey, it's a symmetric histogram. 7's in the middle, the highest probability. Common sense might indicate, yeah, it's probably going to be on average 7, and it is. This is the expected value of this distribution. It's like a predicted average result of doing this experiment. So what this is saying is that, in this experiment of rolling 2 dice and recording the sum, 7 is the expected value. It's not like you're expecting it a total of 7 every time, but you're expecting to get an average of 7 if you did this over and over and over again. So how do we get this expected value? Well, the calculation is like a weighted average. So I'm going to show you what a weighted average is. A weighted average is like an average where you weight certain things higher and certain things count more. So if we go back to our table, the outcome of 2 in 36 times, it happened once. An outcome of 3 happened twice. An outcome of 4 happened 3 times. So it's like if we did 36 rolls, what should happen is we get 1 total of 2, 2 totals of 3, 3 totals of 2 totals of 3, 3 totals of 4, etc., etc. And we can actually just find the average. And instead of just like having 36 things added together, you can kind of write it like this. So we have a total of 2, it happened 1 time. A total of 3, could happen 2 ways. A total of 4 could happen 3 ways. And now that's a long calculation. So I'm not going to write it down here, but you can get a total of 11 2 ways and a total of 12 1 way. So you multiply all of those outcomes by how many times they occur and divide by 36. So this is something you guys could have already done coming in. It's just an average, but since some of those things happen more than once, instead of writing like 4 plus 4 plus 4, it's a lot easier to write that as 4 times 3. It might be worth taking a moment and actually trying that calculation. So what is 2 times 1 plus 3 times 2 plus 4 times 3 plus 5 times 4? And so multiply all those outcomes times how many times they happen. What you should see is that on top, you get a total of 252 over 36, which gives you 7. So you can see that of the 36 possible outcomes of rolling 2 dice, on average, you can expect to get a 7. So you can think of it as a weighted average. There's another way to think of it too, using a formula, and where the higher probabilities are weighted more. So that formula looks like this, and then I'm going to show you how to use it and show that we get the same answer. So this is our expected value formula. So the expected value, so E, of a discrete random variable, capital X, is equal to, so this may be some new notation for some of you guys, possibly. This is the Greek letter capital sigma, and it just basically means sum. So you take all the outcomes, little x, and you multiply by the probability of those outcomes. So different resources might display this notation in slightly different ways, more involved ways. For our purposes, I think this is good enough. It just means multiply all the outcomes times their probabilities and then add all those up. So what would that look like for us? This is why it's sometimes useful to leave them as fractions out of the same denominator. So what was our first outcome? Our first outcome, x, was 2. and the probability of rolling 2 was 1 out of 36. Our second outcome, x, was 3, and the chance of rolling 3, 2 out of 36. And maybe you can see where this is going. Our next outcome was 4, and that probability, 3 out of 36. We're multiplying outcome times probability, and that sigma just means sum. So we're adding all these products up, and don't need to write all of them down. Total of 11 had a chance of happening of 2 out of 36, and 12, 1 out of 36. So what you should notice is that this is the exact same calculation you get as if you just did the weighted average. See, look, you get 2 times 1, 3 times 2, 4 times 3, and they're all out of 36. You get the exact same 2 times 1, 3 times 2. You get the exact same value. In this case, though, we're just using the probabilities. So you still get 252 out of 36. You still get 7. Now, moving forward, we are going to use this expected value formula, and you guys should know this. So outcomes times probabilities and add them all up. But hopefully you can now, the fact we did this as a weighted average, you can make that connection between this calculation gives you an average of what I expect to get. So the expected value for rolling 2 dice is a total of 7. You can expect to get that on average. Let's do a few more examples. We're not going to get crazy complicated today. Our next lesson will analyze some game shows and some expected values, and that should be really interesting. We'll get more involved there. But let's consider tossing 3 coins. So we actually have analyzed this before. To find the probability of flipping, getting no heads or 1 or 2 or 3, we made a tree diagram in the past. And it's not such a crazy big tree diagram that we can just remake it again. Not a big deal. And you can see that at the end, you've got 8 branches, 8 different possible outcomes, like heads, heads, tail, head, tails. And you can see there is 1 branch, all tails, out of 8 that has no heads. In the same way, there's 1 out of 8 that have 3 heads. And then using symmetry, or just by counting them up, there was 3 different branches that have 1 head, and there was 3 that have exactly 2. And those do add to 8 out of 8. Everything's good. We've done this before, but now we've actually, this is the distribution for the number of heads. We've showed the distribution. Now, the one thing we'll do now is, well, what is the expected number of heads when you flip 3 coins? Well, we can use our expected value formula here. So expected value, capital X, is, so the outcomes. So the first outcome is 0 heads, and its probability was 1 out of 8. Second plus, the second outcome was 1. Its probability was, 3 out of 8. 2 heads, 3 out of 8. 3 heads, 1 out of 8. So take a moment and calculate that. You can leave your answer as a decimal if you'd like. And then think about, does that answer make sense? Do I need to round it? If you want to pause the video and do that, and unpause in a minute or so when you have an answer, that's great. Or you can follow on with me. Here we go. So you get 1 times 3 is 3, 2 times 3 is 6, so 9, 3 times 1, that's 12. You end up getting 12 over 8, or as a decimal, that's 1.5, and the value here is heads, right? The expected value here is 1.5 heads. So the question is, should I round that to 2? Should I round that down to 1? And the answer is, it's okay that it's not a whole number. We know we can't get 1.5 heads, but this expected value tells us is that on average, if we flip 3 coins many, many times, on average, you'd get 1.5 heads. You don't need to round it. We know that you can't get 1.5 heads flipping 3 coins. This is a predicted average. So it's okay to be a decimal. Keep that in mind. Let's analyze something we haven't before. So this is a simple dice game where you roll a single die. So in this game, if you roll a 1 to 5, you get double that number of points. And if you roll a 6, your opponent gets 5 times that number of points. So let's see who has the advantage in this game. Maybe it's a fair game where no one has the advantage. So we're going to come up with a distribution for the number of points scored. So we're going to be on team 1 to 5. So we can think of it this way. So if you roll a 1, you get double that amount of points. So if you roll a 1, you get 2 points. And this is going to be our random variable. Capital X is going to be the number of points. If you roll a 2, we get double that. If we roll a 3, we get double that, 8 points. And if we roll a 5, we get 10 points. Now, if a 6 is rolled, our opponent gets 5 times the number, 30 points. So what we can think of that is, from our perspective, if our opponent gets 30 points, in terms of how much we're winning or losing by, it's like we lost 30 points. So you can put a negative 30 there. And because this is we're using a simple dice, the probability of getting each roll is just 1 out of 6. So this is an example of a uniform distribution. If you'd like to analyze if something is a fair game or not, what you can do is find the expected value. And if the expected value here for number of points is 0, it means on a typical roll, I expect to get 0 point advantage on my opponent. Sometimes I'll get points, sometimes I'll fall behind in points, but on average it'll be 0. That's what we're looking for a fair game. So let's find the expected value here and see if this is a fair game. So the expected value, I'm going to write this using a shortcut that you may want to take advantage of. All of these outcomes are over 6. So you can put all of these just all out of 6. And we're multiplying each one of our outcomes by 1 out of 6. So that's 1 times 2 is going to be 2. 1 times 4 is just going to be 4. So it's just like in a uniform distribution, you can just add up the outcome values, 6 plus 8 plus 10 minus 30, and divide by 6. This is for uniform. This shortcut works for uniform only. Of course, we could do it the old-fashioned way, where you do 2 times 1 over 6 plus 4 times 1 over 6, but plus, squeeze this in there, negative 30. I'll take a moment to erase that. Plus negative 30 times 1 out of 6. Get out of there. There we go. Yeah, as I said, we're just shooting from my basement here. We're not gonna edit videos or pause for little things like that. So negative 30 times 1 out of 6. But yeah, you get the same value either way. 2 plus 4 plus 6 plus 10 is actually equal to 30. And 30 minus 30 is 0. So you get 0 out of 6, you get 0. So this is a fair game. Sometimes we'll gain points. Other times our opponent will, and so we'll fall far behind. But what we've shown is that this is a fair game because the expected value is 0. One last example here. Tomorrow we'll do some more game show analysis. Just some examples, have some fun. Most people are familiar with Deal or No Deal. I think we might do a more complicated example of this tomorrow, but they start off with 25 cases. One case has $1 million in it, and the other cases have some have lots of values like 300,000, but some have like a cent or 5 cents, right? And every time the contestant picks briefcases, they open them, and then there's only a certain number left, and then the banker will say, well, hey, you can stop the game right now and I'll give you this money, or you can keep playing and try to get the $1 million. This is a classic application of expected value. So if you guys ever wind up on deal or no deal, you can kind of make educated decisions. But let's look at this scenario. So this player has 5 cases left. The $1, $5, the $3. Oh, so I guess that's four cases left. And oh, there's excuse me, that's okay. Yeah, there's 2 $1 million cases. Reset. Okay. So the banker offers this player $306,000 to stop playing right now. We're going to see what their expected value would be if the person plays to the end and keeps the briefcase. We could also make an educated decision now whether we should take or leave the offer. So we can find the expected value. So this is a uniform distribution. Actually, I guess if they all were different, it would be. But just, if you would like to down below, you can just make a tiny little table, if you like, with outcome and probability. So you can get $1, $5, 300,000, or 1 million. And the chance of getting, there's only 5 cases. There's one of the 5 is $1, one of the 5 is $5, one of the 5 is 300,000, and 2 of the 5 are $1 million. So we can find an expected value here. Outcome of 1 has a 1 in 5 chance of being selected if we go to the end, right? The $5 case has a 1 in 5 chance of being selected, and then 300,000 has a 1 in 5 chance of being selected, and then there's the 1 million has a 2 in 5 chance of being selected. So why don't you guys find that expected value? Is it more than the banker's offer? Is it less than the banker's offer? So let's find out. So you can pause the video and try that, or you can just kind of stick around with me as I just, manually do this as well. 2, 3, plus that'd be 2 million and divided by 5. So I got for my expected value here, 460,000, $1.20. So if this player were to just play to the end until they had 1 briefcase left, on average, they would win about $460,000. Now remember, that is an average. Sometimes 2 out of 5 times they'd win the million, but then 2 out of 5 times they'd also win like basically nothing, $1 and $5. So technically, this expected value, we can expect to win more than the banker offers, but it's not so easy if you're in the hot seat to say whether you take 306 or risk it and try to go for the 1 million or 300,000. The math behind situations like these is actually has a kind of a special name. It's the math of loss aversion, where that has to be factored in as well. Because you're not guaranteed to win that 460,000 on average. There's a chance you might lose everything as well. If you said, well, I would leave the offer because if I keep playing, on average, I'd win $150,000 more. Like, I would buy that. That's good logic with math. But if you'd say, you know what, I think I'll just take the $306,000 because I came with nothing, and I'm leaving with $306,000. And if I keep playing, there's a 2 out of 5 chance that I'll actually wind up with nothing. So I would buy that too. So for the answer of would you take or leave the offer, like mathematically, yeah, maybe leaving the offer is better. Excuse me. But definitely couldn't blame someone for just taking the offer too. And if you'd like to look more up on the math behind this, that is loss aversion. All right, so we've learned about what a probability distribution is, making probability histograms, and calculating expected values. So those my in-class people hopefully have their texts with them. If not, I have a PDF of these practice questions as well that my online class is used to doing as well. Try those, guys. Solutions are posted as well. And yeah, guys, just keep learning, practicing. It's a productive way to fill your time. Helps you stay on top of your course for ultimately when we get back together, hopefully. You're just not you're not too far behind, and learning is the ultimate goal here. So hope you enjoyed that lesson. Come back tomorrow. I should have another one up where we analyze some game shows and expected value. Should be a lot of fun. We'll see you guys online. Have a great rest of the day.